Hello, friends. Welcome back to You Can Do TV. A single field service organization holds $2 billion of spare parts on the shelf. Massive offshore modules get lifted in under 24 hours. One power plant generator rebuild happens once every 30 years and involves replacing coils 330 times over. Behind every industrial machine that keeps a city running sits a repair industry most people have never heard of. Keep watching for the crack that nearly took out 4 turbines at once. A gas turbine at a power plant is worth somewhere between $30 million and $80 million. When one fails, nobody orders a new one. They call a specialized field service team that shows up with cranes, hot gas path tooling, and combustion inspection kits. The team performs rotor unstack and restack, fuel nozzle testing, coating restoration, and full alignment work. Every step happens on site, next to the running plant, because the alternative, tearing out the turbine and shipping it away, takes years the power grid does not have. A field service organization for gas turbines runs on scale most people never see. 7,000 toolkits stocked across 4 depots, and 20,000 different spare part styles held in inventory. $2 billion of parts sitting on shelves because a turbine outage without the right part costs more per hour than the part itself. And behind that inventory sits an army of people who spend their careers traveling to broken turbines. 3,500 skilled craftsmen, 700 technicians. When a power plant calls at midnight because a generator failed, the crew ships out in the morning. They live near the plant for weeks or months until the machine runs again. Which explains why field service technicians spend so much of their lives away from home. The machines never really care what day it is. A North American service organization for rotating equipment operates from workshops totaling 148,000 square feet across Montreal and Quebec. Motors, generators, gearboxes, transformers, anything rotating and critical to a factory or power plant. Field teams stand by 24 hours a day, 7 days a week. The philosophy the industry runs on comes down to one line: repair to eliminate the need to repair again. Every rewinding, every machining pass, every final test aims at the same target, which means the goal is not fixing the machine. The goal is fixing it so hard that nobody has to fix it again for another decade. And then there are the jobs where the whole ship ends up on the to-do list. A 300-meter cruise ship enters a dry dock in Rotterdam. Water gets pumped out, the vessel settles onto hundreds of dock blocks. Steel crews replace 40 tons of hull plate, while painters coat 6,000 square meters of surface, all in 17 days. Another cruise ship arrives at a French shipyard for a 3-week refit. Hull cleaning, propeller polishing, thruster service, and interior updates all happen at once. The ship has to be back at sea for the next voyage, because every empty day at the dock costs more than most people's houses. A Spanish shipyard hosts the world's largest cruise ship for maintenance. The dry dock stretches 186 meters wide, 66 meters across, capable of taking vessels up to 440,000 deadweight tons, 4 cranes rated at 100 tons each service the ship through the entire dry docking window. Middle Eastern yards handle the same scope on tankers, container ships, and offshore drilling rigs at the same time. Steel replacement on aging hulls, propulsion overhaul on main engines, coating renewal on entire underwater surfaces, structural inspection using ultrasonic testing. All of it happens in parallel across several dry docks. Walk through a large repair yard on any given day, and every dock has a different vessel, everyone paying by the hour. And sometimes the ship gets more powerful on the way out than it was on the way in. A seismic research vessel arrives at a Spanish yard for an azimuth thruster replacement, an additional propulsion unit installed on the stern. The old propeller comes off first. A new prefabricated stern module gets lifted into place and welded to the hull. The new thruster follows. 24-hour operations across every trade. When the vessel departs, it moves faster and steers more precisely than the day it was launched. At the smaller end of the scale, luxury yachts get the same treatment as cruise ships. Dry dock inside a covered shed, hull cleaning and anti-fouling paint, applied by hand, propulsion service down to the shaft seal, interior modernization from teak decking to electronics. Owners pay for a level of finish that industrial customers never ask for, which is how a yacht repair yard ends up doing rougher work at higher standards than most factories on land. And the customer notices every polish mark. Now the story gets underground, into the engine room. 2 new medium-speed diesel engines get installed on a Greek ferry. Each engine lands on its foundation, gets aligned to the gearbox using laser targets, and gets chalked into the position with epoxy resin poured under precise conditions. Align them off by 0.05 millimeters, and the crankshaft cracks. A cruise ship engine block gets swapped after a failure. Shell plate cut, bulkhead removed. Old engine skidded out. Bulkhead welded shut, shell plate closed. Paint applied, cried, welded shut. Shell plate closed. Paint applied. But most marine engine work stays inside the ship because the parts are too big and too heavy to move. The stuffing box seals the piston rod as it slides in and out of the crankcase. Scraper rings and sealing rings sit inside it. Every ring gets measured with feeler gauges. Any ring worn beyond specification gets replaced with a new segment. The whole assembly gets rebuilt on a temporary work table set up right next to the running engine block, which is a strange kind of surgery. The patient stays on its feet the entire time. The piston itself gets pulled up through the top of the cylinder liner, crankcase door removed, crosshead turned down, stuffing box screws released, piston rod screws removed, lifting tool clamped to the piston crown, overhead chain block hoists the whole assembly clear of the liner. Once the piston is out, the piston skirt comes off the piston crown. Locking wires cut, connecting bolts removed. Piston rod lifted away from the skirt. Sealing ring extracted from between the 2 halves. Every component gets cleaned, measured, and inspected before anything goes back together. And now, the operation that takes 3 weeks and cannot be scheduled twice. A 12-ton crankshaft, 7.5 meters long, gets swapped inside a cruise ship at berth. The hull gets cut. The 80-ton engine block gets jacked up 1.9 meters using hydraulic supports. The old crankshaft slides out. The new one goes in. A cruise ship enters dry dock in Dubai for a 13-day modernization. The 2 massive propellers get swapped for more efficient models, cutting fuel consumption by up to 7% across the ship's lifetime. Hull gets high-pressure washed. 12,960 liters of new paint applied. The signature name on the hull gets laser etched at night for precision. Every step happens in parallel across hundreds of workers. When the dry dock floods on day 13, the ship is faster, cleaner, and quieter than the day it arrived, which is a rare thing to say about anything that's spent 3 weeks in a hospital. Some repairs have to be done on shore. Turbochargers are rebalanced. Fuel injectors are tested to make sure they work properly. Cylinder liners are machined back to their correct shape, and ultrasonic cleaning tanks strip away oil and carbon much faster than manual scrubbing. After every major overhaul, the engine runs on a test stand or at the pier for hours before shipment. Technicians monitor oil pressure, cylinder pressure, exhaust temperature, and vibration signatures on each cylinder. Smoke gets checked at the exhaust under load. Any anomaly, even a small one, triggers another disassembly to find the cause. Sending a rebuilt engine back to sea without proving it works is the kind of decision people write books about later. And now the operation where a few millimeters decide everything. A 32-megawatt industrial generator arrives at a workshop for inspection. The rotor alone weighs 45,000 pounds. The radial clearance between rotor and stator sits at 0.75 inches, meaning the entire extraction has to run within a margin thinner than most phone cases. A custom 20-foot steel tube, weighing 3,300 pounds, gets slid through the rotor to support it during removal. Two 50-ton cranes lift together. The rotor floats out inch by inch until it clears the stator. One bad move and everything on both sides gets destroyed at once. Another 60-ton generator arrives at a repair facility on a 9-axle truck trailer. The tail end of the trailer needs its own driver. The rotor gets extracted from the stator while the generator is still on the truck bed. Two cranes work in coordination. The entire operation runs on radios and hand signals. Once the rotor is out, the real repair begins. A damaged rotor shaft gets replaced entirely. The old shaft comes off in a machining bay. A new shaft gets machined to exact dimensions, then heat shrunk into a rotor core using precisely controlled temperature differentials. Once cooled, the interference fit locks the shaft into place with more holding force than any bolt could provide. Balancing follows on a dedicated balancing pit. Because a rotor spinning at 3,600 revolutions per minute with 0.1 millimeter of imbalance shakes hard enough to destroy its own bearings within hours. A 50-foot industrial lathe machines a 10-foot diameter armature. The chuck alone measures 10 feet across with 4 jaws. Machining tolerance holds at 0.005 inches across 3-foot lengths. This is the machine that finishes what the crane started. And once a rotor is out, the shaft itself becomes the next patient. A 203-inch Kaplan hydroturbine shaft arrives at a shop for refurbishment, inspection, magnetic particle testing, old sleeve removal, precision machining. A steel mill roll comes in with a broken shaft. The damaged section gets machined off. A new shaft, 91 inches long, 3,500 pounds, gets machined from alloy steel, then cryogenically shrunk with liquid nitrogen and pressed into the roll bore for a permanent interference fit. A 3,000 horsepower motor armature gets a brand new shaft installed. No original manufacturing drawing existed. The team reverse-engineered the part from measurements, machined it, chilled it, and slid it into place cold. Some shafts weigh more than most trucks, and they still get resurfaced without buying new ones. A 22,000-pound propulsion shaft gets fitted with new brass sleeves at the bearing journals. Each sleeve gets heated, expanded, slid into position, and shrunk back onto the shaft within a tolerance of 0.5 millimeters. Hydroelectric wicket gates get restored through thermal spray. A 420 stainless steel coating gets sprayed onto worn journal fits at bond strengths up to 10,000 pounds per square inch, restoring the surfaces to original factory specifications. Inside a 54,000 square foot component repair facility, gas turbine parts pass through 20+ separate processes: reverse engineering by 3D scanning, hydrogen fluoride cleaning, high-speed electrical discharge machining, automated shot peening, controlled atmosphere welding, vacuum heat treatment, robotic thermal spray coating, fluorescent penetrant inspection, pulse thermography, coordinated measuring machine dimensional verification, dynamic flow testing. Every stage exists because a new turbine blade set costs several $1 million, and the repaired version has to run at exactly the same temperature and stress as a brand new one. And when the whole steam turbine comes apart, thousands of individual pieces have to be tracked separately. A large industrial steam turbine gets fully disassembled at a repair facility. Rotor lifted out, stator inspected, bearings removed. Every blade tagged and photographed. Diaphragms measured for warp and cracking. Any component out of specification gets machined, coated, or replaced entirely. Reassembly then reverses the whole thing in the exact opposite order. One wrong bolt in the wrong hole, and the turbine spends its next life as scrap metal. New steam turbine blades get installed on site at the repair facility before shipment back to the customer. Blade root fits get checked with feeler gauges. Blade tip clearances get measured against original specifications. Each blade gets torqued and locked into place, which is quieter work than it sounds until it starts spinning. Viewers see the rotor turning. What they never see is the thousands of meters of copper wire hidden behind it. A specialty shop manufactures robo bars and coils for medium and high voltage motors and generators. A large industrial generator arrives at a specialized shop for a full stator rewind and core rebuild. The generator gets disassembled. Old copper coils get pulled from the slots. The iron core gets inspected lamination by lamination and rebuilt where damaged. New coils get manufactured, insulated, and inserted into the stator slots, one at a time. Electrical testing follows before shipment. The whole job takes months. The copper alone runs longer than most highways, and every meter of it has to survive 30 years of running hot. A hydroelectric generator at a Malaysian power station suffers a stator fault and gets shipped for full rewind and uprating. The damaged core sections get repaired, new stator bars get manufactured, tested, and installed. The rotor gets rewound separately. Post-installation testing includes high-voltage insulation, bar-to-bar checks, and full load verification. When the generator returns to service, output capacity increases by 12%. The same machine doing more work, running cooler, expected to keep running for another 2 decades. At Bliss Power Plant on the Snake River, a full generator rebuild happens roughly once every 30 years. Crews replace each copper coil in the core one at a time, driving wedges, tying coils back, then repeating the process 330 more times. A large motor that powers a pump at Pearl Harbor arrives at a rewinding facility. The old windings get burned out in a controlled oven. Copper coils get manufactured on-site from spools of insulated wire. Slot liners get inserted, coils get hammered into position and wedged. Connections get braced together. Then the entire stator goes into a vacuum pressure impregnation tank. Vacuum applied first to remove air, then epoxy resin forced into every gap under pressure. The whole thing comes out looking like a machine dipped in glass. At a General Motor rewind shop, the variety of work covers everything from small pump motors to 5,000 kilowatt generators, random winding for multi-strand stator coils, layer winding for rotating field coils, lamination replacement on damaged generator cores, commutator undercutting using laser-guided tools, coil insertion and slot wedging. Final testing checks all 3 phases of output voltage on rebuilt generators. Any phase reading off by more than a fraction of a percent triggers another disassembly. Motors do not tolerate approximation. They tolerate specification. Traction motors from trains and locomotives arrive at a specialized rewind shop for full armature rebuilding. Old windings get stripped. New commutators get installed. High voltage pressure testing verifies the armature can hold electrical isolation. Bar-to-bar tests check every commutator segment. New coils get inserted, wedged and TIG welded to the commutator segments. Vacuum pressure impregnation with epoxy resin follows. Banding, balancing, and final dial indicator checks confirm the armature runs true, because a wobbling traction motor takes down whichever train it happens to be under at the time. A 360 horsepower 3-phase motor with a wound rotor gets sent in for stator rewinding. The old copper windings get removed. Insulation strips get laid into the stator slots. New copper wire gets processed through forming machines and shaped by hand into precise coil configurations. The coils go into the slots. Brazing joins the electrical connections. Impregnating varnish gets poured into the stator and brushed onto every coil. The rebuilt rotor gets balanced on a dynamic balancing rig before final assembly. A community wind turbine generator suffers an earth fault and gets sent in for full stator and rotor rewind. 50 miles of continuous copper wire has to be wound without a break. And these machines are not sitting in museums. They are running power grids. The Yukon Hydroelectric generator goes through a 10-year scheduled overhaul. The unit gets fully disassembled, rotor lifted, stator inspected, bearings replaced, windings tested. Every component measured against original factory drawings. Reassembly then runs in exact reverse order. When the generator comes back online, the local grid has just recovered several megawatts of continuous capacity, which in the Yukon is enough to power around 1,000 homes without anyone even noticing what happened. And sometimes routine monitoring saves an entire power grid. At Rocky Reach Dam on the Columbia River, plant operators notice oil around a shaft and metal shavings in the strainer. Investigation reveals a crack in a 16,000-pound piston rod, a design flaw across 4 large turbines. A dedicated small gas turbine repair, an overhaul facility in Aberdeen handles turbines from oil and gas platforms, remote power stations, and district heating plants. Rotors get disassembled and rebalanced. Blades get inspected under fluorescent penetrant testing. Combustion sections get rebuilt with new burners and thermocouples. Compressor casings get machined for seal fits. Every turbine that leaves the facility has been tested to full power on the test stand before shipment, because sending an unproven turbine back into a producing gas field is the kind of decision that ends careers. A 35,000 square meter facility in Torino, Italy, handles both new gas turbine manufacturing and complete repair operations. Rotor balancing on high-precision machines, vane segment machining underwater to control heat. Non-destructive examination under ultraviolet light reveals cracks invisible to the naked eye. Vacuum heat treatment restores material properties. Automated laser cutting shapes, laid forms. Precision assembly of finished rotors follows every component check. More than 350 gas turbines have shipped from the facility, totaling over 12,000 megawatts of power generation worldwide. Every one of those turbines is now somewhere providing electricity to a city that has no idea where its power actually came from. A 16.5 megawatt power plant. Generator goes through scheduled maintenance. Rotor pulled out, stator and rotor windings cleaned, bearings checked and measured, remaining life assessment performed on the insulation, wedges checked for tightness, bump test performed on the end windings to identify loose sections, then revarnishing of both rotor and stator. Post-maintenance electrical testing verifies the machine can hold isolation at operating voltage, plus a safety margin. Rotor gets reinserted into the stator with millimeter tolerances. A power plant does not schedule this work casually. It schedules it once and prays. A Faroe Islands wind turbine hub arrives for full overhaul. Bearings inspected, pitch motors tested. One extra bolt discovered in a bearing, prompting complete replacement instead of partial repair. The engine gets all the attention, but the reduction gear is what actually turns engine power into ship movement. An LNG carrier enters a Spanish yard for complete reduction gear replacement. Old gears get dismantled. The main gear alone weighs 36 tons. High-pressure and low-pressure turbines get overhauled in parallel, bearings remetallized, rotors balanced during installation. The shaft line is found to be misaligned. Additional docking periods get added to correct it. Sea trials follow, and the ship departs faster than it arrived. Cracks appear in the bedplate of a large tanker's main engine, the massive steel structure that supports the entire diesel unit. The vessel comes in for complete bedplate replacement. Cylinders, cylinder heads, and internal components get stripped. A specialized lifting frame raises the upper engine and crankshaft 340 tons in total using hydraulic tensioners. The damaged 60-ton bedplate slides out on Teflon guides. A new bedplate slides in. Crankshaft gets lowered back onto bearings. Reassembly follows. 70 days from arrival to sea trials. A time-lapse follows the assembly of a portside reduction gear for a Royal Saudi Navy corvette. The gearbox housing sits on a platform. Workers install shafts and bearings. The main gear gets lowered by crane. Auxiliary lubrication and control systems get connected. Every gear tooth gets inspected before mesh. Reduction gears at this scale run for decades under constant load. Every tooth face has to survive 25 years of alternating stress because a broken gear tooth at sea does not get replaced. The ship gets towed home. A CNC spindle repair facility maintains ready-to-ship replacement spindles for 1 to 2 day delivery to customers experiencing spindle failure. A precision spindle motor gets disassembled for bearing replacement, TIG welding, grinding, and electrical testing. Post-repair electrical testing includes resistance, inductance, insulation, and surge peak measurements. And behind every repair yard sits a much older kind of factory, one that both builds engines and rebuilds them decades later. A diesel engine production unit in Cartagena has delivered over 2,500 engines since 1947, the equivalent of 5 million horsepower currently running around the world. The 7,000 square meter foundry casts up to 60 tons of nodular graphite iron per pour. Assembly lines cover 5,000 square meters. 9 test beds handle propulsion and generator engines. Because building an engine is one job, keeping 2,500 of them running for the next 40 years is a completely different one. The foundry casts engine blocks and cylinder heads for every major diesel engine the factory produces. Chemical bonded sand molds get formed from silica sand mixed with resin. Coating gets applied to the mold surfaces to improve finish quality. 3 induction furnaces melt gray and nodular iron. Casting temperature gets measured at each pour. A dedicated laboratory analyzes chemical composition of every melt in real time. Finished castings then move to a heat treatment furnace, because raw cast iron is brittle and heat treatment is what makes it a working engine block.
Modern shipyards integrate 13 digital technologies across production. Autonomous robots on the shop floor, augmented reality overlays for assembly guidance, predictive maintenance based on real-time sensor data, every step traceable from the design office to the shop floor. Time-lapse of the second Suez Max tanker built at the same yard, every phase compressed into minutes, hull sections lifted by cranes, superstructure assembled overhead, interior fitting completed in parallel. The same yard that builds new ships also runs the repair dock next door, which is how the industry actually works. The same welders who build a hull today rebuild a different hull tomorrow. Nothing gets thrown away that can be fixed. A specialized rail traction motor division handles alternating current and direct current motor repairs for train fleets, full overhauls, alternator testing under simulated full load conditions, life extension services that keep 30-year-old trains running for another 15 years without any performance loss. A general repair facility handles motors, generators, pumps, and gearboxes across every industrial sector: mining, power generation, water treatment, marine, oil, and gas. 24-hour emergency call-out, 365 days a year, because critical rotating equipment does not fail during business hours. The repair industry rebuilds machines that already work. That is a strange business model, until you realize a rebuilt gas turbine at 40% of new cost, delivered in 6 months instead of 3 years, keeps a city's lights on that would otherwise go dark. The economics of overhaul are the economics of infrastructure survival. But the field faces a real problem. Most experienced overhaul specialists are retiring, and few young workers are entering the trade. Every skilled hand that leaves takes decades of unwritten knowledge with them, which raises a fair question. Can the industry train skilled overhaul workers fast enough to keep up with the growing demand? Drop your view in the comments. Thanks for making it to the end. Every new video goes deep into a corner of industry most people never see. Subscribe if that is worth your time. Take care.